Hello students, welcome back to SapphireBlueChemspark. Let us start our today's session from Inorganic Chemistry, the chapter D and F block elements. So, the last session we discussed about the introduction of D and F block element, where we discussed about the position of D block as well as F block. Also, we discussed about atomization enthalpy, metallic character, melting point, boiling point and all. And we said the atomization enthalpy is due to the greater number of unpaired electron that makes greater metallic bonding, and hence the atoms are said to be so strong or very hard. So here what do you mean by atomization enthalpy? Atomization enthalpy is nothing but removal of an atom from metallic lattice, for which a particular amount of energy is required. So the amount of energy that depends upon the nature of bonding present in the crystal lattice. If at all the bonding, metallic bonding is much higher, then the amount of energy required for that will also be much stronger or much greater. So atomization enthalpy is denoted by del H A. A denotes atomization enthalpy. So this is the amount of energy is required to isolate an atom from the crystal lattices of metal, and in this case the second and third period they possess very high atomization enthalpy compared to the first transition series. So that indicates second and third transition they possess very strong metallic bonding, and hence they do have their greater melting point. So the melting point, boiling point is nothing but the function of atomization enthalpy. When the interatomic distances is much smaller, as well as the bonding between them is very high, and then they need to break the forces of attraction, very high energy. That's why they have high melting point as well as boiling point. So today we are going to discuss about atomic and ionic radii as well as ionization enthalpy. What do you mean by atomic radii? Atomic radii is the distance between the center of the nucleus to the outermost electron. So we can say that is what the valence shell cloud. So atomic radii is defined as the distance between the center of the nucleus to its outermost valence shell, that is called atomic radii. So when you consider an atom, it has an electron boundary between the atom and the valence shell. But at the same time, when we consider ionic radii, what would happen? Whether we would have removed an electron or we could have added an electron. By that condition, they can become a cation or an anion. So how to define the ionic radii? We have to say the distance between the center of the nucleus and the electron cloud to which that electron cloud can experience nucleus forces of attraction, that is said to be ionic radii. So how this atomic and ionic radii, they vary in their transition series. Actually, the transition element that is lying between S block and P block. So in the periodic property, atomic and ionic radii that decreases along the period. Why it is decreasing? Because when we go from left to right of the periodic table, every electron, whenever it enters into the valence shell, and a proton will also be added to the nucleus. So the effective nuclear charge increases, and hence the forces of attraction also increases. So the nucleus that can attract the valence shell towards itself, that's why the atomic radii as well as ionic radii decreases along the period. So as the newly entered, as the differentiate electron enters into the same shell and it correspondingly increases the nuclear charge, therefore the forces of attraction gets increased. This is the reason why atomic radii decreases along the period. Okay, so when we said it decreases along the period from left to right. So the S block elements have higher atomic radii compared to P block element. So atomic radii of S block element is greater than P block or even D block. What about D block? D block elements, they have smaller atomic radii than S block but larger atomic radii than P block. Now let us compare the atomic and ionic radii of the different transition series. So in this graph we have plotted atomic number against radius. Radius is taken in nanometer. So the first transition series we may find the initial beginning of the element, they have almost constant atomic radii and it decreases, then once again it increases towards the end of the series, the first transition series. This is why, because initially the number of unpaired electron increases from scandium to manganese. So scandium we have D1 and manganese we have D5. After manganese till zinc, what happens? The D5 it becomes a D10 as far as considering the zinc. So what happened? The d orbital after crossing the manganese, it gets paired up. So when we move from iron to zinc, the electronic repulsion that causes the increase in the atomic radii of the end of the series. So this is because both of the electrons are being added to the same orientation. So that may cause electron repulsion. That's why the electron cloud as far as it increases and hence atomic radii also increases. The next one, when we compare the atomic radii of second and third transition series, you may find both of them have almost similar atomic radii. This is why in the first transition series we said the 3d orbital is being filled up, and in the second transition series actually the 4d orbital is being filled up, and the 3d orbital that belongs to n equal to 4 and 4d that belongs to fifth period. So the third transition series actually it commences in sixth period. We know well, when it opens the sixth period, you may find the lanthanum actinium are there. After lanthanum, cerium to lutetium, and after actinium, thorium to lawrencium we have. So what happened? Before filling of the d orbital, the f orbital gets filled up. And these f orbital, they have very poor screening effect compared to d orbital. So due to the poor shielding effect of f orbital, that also increases the nuclear forces of attraction over the valence electron. Therefore there is a reduction in the size of the entire series of atom, that is called lanthanide contraction. So this lanthanide contraction once again we will discuss in detail when we take the topic F block elements. So we can say second and third transition series, they have almost same atomic ionic radii. This is due to the imperfect shielding of 4f orbital in the third transition series that cause total reduction in the size of their third transition series. Therefore, the atomic radii of second transition series, it shows similarity with its third transition series. We can compare that zirconium as well as hafnium. Both of them, they have 159 and 160 picometer only. So zirconium, hafnium belongs to 6th period and zirconium belongs to fifth period. So this is 6th period element, this is 5th period element, but they have similar atomic radii. This is why, because the 4f in hafnium, the 4f orbital gets completely filled. After that only the 5d orbital being filled up. So this is why second and third transition series, they have similar atomic radii compared to first transition series. So you can find the reason for the decrease in atomic radii of the first transition series followed by increasing is just because of the increasing nuclear charge that gets cancelled by increasing screening effect of electron in d orbital. That's why atomic radii almost constant when nuclear charge cancels the screening effect of d orbital. After that only the atomic radii increases. This is because the electronic repulsion among the paired electrons of d orbital. That's all atomic and ionic radii of the transition series. The next periodic property of transition element is ionization enthalpy. What do you mean by ionization enthalpy? Actually, ionization enthalpy in which the cations are formed by the loss of electron. So, how it can be removed? So, ionization enthalpy is defined as the amount of energy which is required to remove a loosely bound valence electron from the neutral isolated gaseous atom. So, this involves the three different enthalpy. One is it requires atomization enthalpy because we have to isolate an atom from the crystal lattice. Second one, the atom which is in solid state to be converted into its gaseous state. So that requires sublimation enthalpy. After the gaseous state, there only you can remove the electron. It requires ionization enthalpy. So the amount of energy required for the ionization enthalpy is the sum of all the three. So when we consider about the ionization enthalpy as a periodic property, this ionization enthalpy along the period increases. Why it is increases? We said across the period effective nuclear charge increases. So when effective nuclear charge increases, the entire valence electron will be under the great influence of the nucleus. So it is not possible to remove the valence electron so easily. That's why across the period, as the effective nuclear charge increases, ionization enthalpy also increases. So what about the ionization enthalpy of d block element? The ionization enthalpy of d block element which lies in between of S block and P block. But S block element they can form either a positive ion or a dipositive ion only because it has one electron or two electron in its valence shell. But in this case the number of valence shell that increases. Anyhow we can able to remove up to maximum of 3 electrons only. So when you remove the first electron, it is said to be first ionization enthalpy. When you remove the second electron, where the atom that becomes an ion. So from the ion, when you remove the electron, what happened? Very high nuclear charge will be there. That's why the removal of electron becomes highly difficult, and hence the successive ionization enthalpy becomes greater than the previous one. So here we are comparing only the first ionization enthalpy of S block elements, D and F block element with P block element. The S block they have lower ionization enthalpy compared to P block. Therefore, the D block it has higher ionization enthalpy than S block but smaller ionization enthalpy than P block. Okay, what about that ionization enthalpy of the transition series? We can have the different graph for the three types of transition series where we plot against the atomic number against the ionization enthalpy. So the first transition series it is given over here. Initially the titanium, vanadium, chromium ionization enthalpy slowly decreases. This is why because they are all having only one electron, that is single electron, they have unpaired electron in it. So in this case the effective nuclear charge is smaller. But when it increases, what happens? Number of electron entering to n-1 d orbital increases, where effective nuclear charge increases as well as the d orbital that has a very poor shielding effect that also increases. increases. So, the increase of effective nuclear charge is partly cancelled by the increase of screening effect of d orbital, and hence towards the end of the series the ionization enthalpy increases. At the same time, the third transition series element, they possess very high ionization enthalpy compared to first and second. Once again, this is because of the filled orbital getting 4f orbital. So, before filling of the d orbital, the 4f orbital gets completely filled as it belongs to 6th period. And these 4f orbital, they have very poor shielding effect compared to d orbital, and hence because of the imperfect shielding of 4f orbital, effective nuclear charge increases, and hence ionization enthalpy for third transition series is also increases. Then what about the significance of ionization enthalpy? By knowing the ionization enthalpies of the different metals, we can identify what kind of salts can be stable or unstable. Let us consider the ionization enthalpies of nickel and platinum. In this, nickel can have +2 state as well as +4 state. That means in the initially it can lose either 2 electron or the nickel can lose 4 electron. Similarly, platinum is also taken in its +2 and +4 state. So, how many times you are removing the electron, that many time ionization enthalpy increases. And I told the successive ionization enthalpies are very high. So, when you add the first and second ionization enthalpy of nickel 2+, it is found to be 2490 kilojoule per mole. When this amount of energy is compared with platinum 2+, see it has 2655 kilojoule. So, as the ionization enthalpy of platinum 2+ is greater than that of nickel 2+, we can say nickel 2+ salts are stable than platinum 2+. What do you mean by nickel 2+, platinum 2+? For example, I can write nickel chloride as well as platinum chloride. So, nickel chloride is more stable than platinum 2 chloride. And now we are going to compare the +4 state of nickel and platinum. So, +4, it has to remove the 4 electron. So, the sum of first, second, third and fourth ionization enthalpy, that equals to 11,182 kilojoule per mole. But that of platinum is simply 9605 kilojoule per mole. Here also the platinum, it has very low energy compared to nickel, and hence platinum 4 salts are more stable than nickel 4 salts. So we can write platinum Cl4 is more stable than NiCl4. So this is what the significance of ionization enthalpy. From the knowledge of ionization enthalpy, when we find that sum of all the ionization enthalpy, if at all the value is smaller, then their respective salts will be more stable. Factors that determine the stability of the particular oxidation state of metal ion is the enthalpy of atomization and hydration enthalpy. So, in the previous case, we studied about what about the stability of salts according to the sum of their ionization enthalpy. When an atom loses the electron, that gets corresponding positive charges. Those positive charges, we can say it as the oxidation state of the metal ion. So, during the formation of the metal ion, they can able to stable in its oxidation state if at all the sum of ionization enthalpy, atomization enthalpy and hydration enthalpy is smaller. So, the total enthalpy change, if at all smaller, then the particular oxidation state is said to be more stable for the particular metal ion. So the sum of total enthalpy change, that is equal to the sum of ionization enthalpy, atomization enthalpy and hydration enthalpy. So this value must be smaller, and hence the metal ion in its oxidation state is said to be more stable. We know what is ionization enthalpy as well as we know what is atomization enthalpy. What do you mean by hydration enthalpy? Hydration enthalpy is always it is an exothermic process. Hydration enthalpy is always an exothermic process. That means during the dissolution of a salt in water, some amount of energy is released. That is called exothermic reaction. In this case, the metal ion that produced in the solution can be solvated by the water molecules. So, the amount of energy released during the solvation of 1 mole of ion by water molecule is said to be hydration enthalpy. So, the hydration enthalpy, if at all negative, then we can say the salt is more readily soluble in water. If hydration enthalpy becomes positive, then those salts are said to be sparingly soluble in water. The next general property of D block elements is oxidation state. This oxidation state actually depending upon the number of valence electron present in the given element. So when we go from the third transition series scandium to zinc, actually scandium to manganese, number of unpaired electron increases in d orbital from 1 to 5. After manganese, the number of unpaired electron decreases because the electron is being paired up from iron to zinc. That's why the lower end of the transition series as well as the upper end of the transition series, they have only one oxidation state. Scandium, it has the electronic configuration of D1S2. So, both of the electron being removed. So, we are getting +3 state for scandium. But when we go to zinc, it has completely filled d orbital and 2 electron in its s orbital. Only these 2 electron can be lost by the zinc, and hence it can have only the +2 state for zinc as well as +3 state for scandium. But when we go to titanium, you may say the s orbital electron is first of all being lost for the oxidation state, followed by the loss of the d orbital electron. So, we said the d orbital electron getting the unpaired electron increases from 1n to the middle of the series. So, in this case, if I consider this is for an manganese, d orbital has 5 unpaired electron and s orbital has 2 electron. So, manganese, if at all it loses only the s orbital, it can have the +2 oxidation state. Or if it removes all the 7 electron, then it is said to be +7 oxidation state. So manganese, it can have the lowest oxidation state of +2 as well as the highest oxidation state of +7. So the metal, whenever in its higher oxidation state, is usually behaving as strong oxidizing agent because they tend to reduce themselves to achieve their lowest oxidation state, because in this lowest state only they will find its stability. When we consider chromium, its atomic number is 24. So we can write this chromium that can have 4 electron in its d orbital and 2 electron in its 4s orbital. So that can have the stable oxidation, the lowest stable oxidation state is +3 and the highest oxidation state is +6. +6 as a result of loss of all the 6 electron from the orbital. The +3 state, it is because of the d orbital being partially filled. Actually, d orbital orbital, it has two sets. One is said to be T2G and the other one is said to be EG. So in the T2G it has 4 electron and EG orbital has 0 electron. And in this, the T2G it has 3 orientation and EG it has 2 orientation only. So when you find 4 electron in T2G orbital, we have to write 1, 2, 3, 4 like that. If at all chromium loses the 4s electron as well as one of the T2G electron, then it changes into T2G3, that becomes a half filled orbital. Therefore chromium, instead of losing the 4s electron, it loses one more electron from the d orbital and hence it achieves its +3 oxidation state. If at all the 6 electrons are lost, then its highest oxidation state will be +6. So this is the reason potassium permanganate and dichromate are used as the strongest oxidizing agent, because both of them are in their higher oxidation state. When they are reducing, they will reduce to their lower oxidation state of +3 in case of chromium and the lower oxidation state of +2 in case of manganese. So, how this oxidation state varies? You may find the oxidation states, they are differed by only one unit when you compare the transition elements. At the same time, when this oxidation state of transition element compared with the p block element, what happened here? On moving down the group, the oxidation state that differs by the unit of 2. This is why, because the p block element, they have the valence shell ns2np126. On moving down the group, the 2 electron present in ns orbital becomes inert. Only the electron present in p orbital takes part in its chemical reaction. That effect is known as inert pair effect. So because of inert pair effect of ns orbital, then the p block elements, they have their oxidation state with the differing value of 2. For example, if I consider the 15th group element, it will have +5 state and +3 state. So the +5 state will be more stable at the top of the group. But when you go down the group, the stability of +3 state increases. This is because the inert pair effect of ns orbital. Then this transition elements, in this, the first transition series, we observed that manganese only can exhibit the highest oxidation state of +7. The other transition series, second and third, they able to exhibit even the highest oxidation state of +8. Example as osmium, ruthenium and rhodium, those and all able to form the +8 oxidation state. So here the oxidation state is nothing but why d block element, they provide too many number of variable oxidation state. This is because of the large number of valence electron present in its n-1 d orbital and ns orbital. And the oxidation state that shows its highest value only to the middle of the element. From the right to the middle or left to the middle, their oxidation state decreases. This is the reason to the left of the middle element, the number of unpaired electron is less. To the right of the middle of the element, the number of unpaired electron decreases. This is the reason when the element have too many number of electron in its valence shell able to exhibit the highest oxidation state, the metals with the least number of unpaired electron or the more number of paired electron, they used to exhibit the lower oxidation state. And in this case, some of the oxidation states are given in the open parenthesis. It is said to be their unstable oxidation state. Though those elements form their compound in such oxidation state, immediately they will change into their stable oxidation state either by decomposition or by disproportionation reactions. Based on ionization enthalpy, we can have some reasoning questions. One of the most important reasoning question is the third ionization enthalpy of manganese is greater than that of Cr3 plus, chromium 3 plus. So let us discuss both of them. So we said the third ionization enthalpy of manganese is found to be much greater. This is what the Mn3 plus ion whose ionization enthalpy is 3260 and Mn2 plus whose ionization enthalpy is 1509. For Cr3 plus its ionization enthalpy is 2990 kilojoule per mole. So when we compare the third ionization enthalpy of chromium with that of manganese, we may find chromium 3 plus it has 2990 and that of manganese 3 plus is 3260. This is why in manganese actually it has 25 and its electronic configuration is 3d5 4s2. So the first 2 electron it is being lost by only the 4s orbital for which the ionization enthalpy is found to be 1509. It is the second ionization enthalpy. Now when it removes the third electron, then it must be removed from the half filled 3d orbital of manganese. We know well the half filled and completely filled orbitals are much stable. They have got great extra stability because of its half filled and completely filled. So when you remove the electron from the half filled orbital, because of its extra stability, the energy required to remove the electron goes increases. At the same time in chromium actually it forms the +3 state. In this case, it is found to be 3d4 state and the d orbital it has 2 sets because d orbital we have dxy, dyz, dzx, dx square minus y square and dz square. So these are making 2 sets of orbital. One is T2g set, the other one is said to be EG set. Why do we classify d orbital such a way? Because of their orientation of lobe. In this case, the lobes are along the axis, but in this case, the lobes will be in between of axes. So because of the variation in their lobes, we are getting the 2 different types of d orbital, T2g and EG. Usually the T2g is said to be in low energy and EG is said to be in high energy. So when you compare chromium 24, d orbital has 4 electrons in its orbital and all the 4 electrons are present in T2g set. Once the 4th electron of the T2g is removed, then T2g it becomes a half filled orbital. So to attain the extra stability of chromium from +2 to +3, it is ready to lose the 4th electron in order to get its extra stability. But in the case of manganese, already it has the stability, but when you remove the electron from the more stable, sure they will get high energy for that, and hence the third ionization enthalpy of manganese is greater than chromium 3 plus. When they ask about that reasoning question, you have to consider the stability of the d orbital, whether they have half filled or completely filled. Such a way only the answers has to be presented for the reasoning questions. Okay students, let us close our today's session. So we discussed about ionization enthalpy, atomic radii, ionic radii and the oxidation states of transition metals. Let us close our today's session and we will continue the same chapter in our next session. Until then, bye bye.